Welcome to the course on an introduction to information theory. I am Adrish Banerjee. Today we are going to talk about how to do source compression for sources with memory. So far we have discussed source compression algorithm for sources which are discrete memoryless sources, right? So sources, but in general the sources that we see in nature have memory. So can we exploit this memory while doing source compression? That's what we are going to talk about today. So before we discuss about that, we'll first define what do we mean by a discrete stationary source with memory. Once we describe this discrete stationary source with memory, we are going to describe how we can do. We'll take a simple example of block to variable length coding. So how we can do block to variable length coding for a discrete stationary source, and we'll prove some properties of discrete stationary source. We'll talk about a particular coding scheme which is known as Elias-Willems source coding algorithm, and it uses a technique to code positive numbers. So we'll talk about how can we code positive numbers using a prefix free code, and we are going to use that to design Elias-Willems source coding scheme, which is a block to variable length source coding scheme for a discrete stationary source. So what is a discrete stationary source? So as you can see, it's discrete and stationary. So a Carey discrete stationary source emits a sequence UI which consists of Carey random variables such that for every n greater than equal to 1 and every L greater than equal to 1, the random vector denoted by U1, U2, U3, UL and random vector UN plus 1, UN plus 2 up to UN plus L, they have the same distribution. So it does not matter what n is. N can be 2, 3, 5, 100. If this random vector and this random vector has same probability distribution, then it has a stationary, basically it's a stationary source. Okay. Now we say a discrete stationary source to have a finite memory mu if for all n greater than equal to mu we can write probability of un given u1, u2, un minus 1 if it only depends on past mu values. So probability of un given un minus 1, un minus 2, u2, u1 is if it's same as probability of un given un minus 1, un minus 2 up to un minus mu for all choices of u1, u2, then basically we say that this particular source has a finite memory mu, and mu is the smallest non-negative integer for which this relation holds. Okay. Now as you can see, the discrete memoryless source that we have considered so far is a special case of discrete stationary source which belongs to the case when mu is 0. Now it's not very difficult to prove that for a discrete stationary source with memory mu, the uncertainty in un given u1, u2, un minus 1 is equal to uncertainty in un, entropy un given un minus 1, un minus 2, un minus mu. This follows directly from the property that we stated earlier, that if if you have a discrete stationary source of memory mu, it's going to satisfy this condition, that probability of un given u1, u2, un minus 1 is same as probability of un given un minus 1, un minus 2, un minus mu. So from this, and applying the definition of entropy, we can directly get this relation, that for a discrete stationary source with memory, uncertainty in un given u1, u2, un minus 1 is same as uncertainty in un given un minus 1, un minus 2 up to un minus mu, where mu is the memory of this discrete stationary source. And this is true for all n greater than mu. Now, how do we define uncertainty for a discrete stationary source? So there are two ways we can describe it. One way we can describe this uncertainty per letter. So this is defined as follows. So uncertainty per letter is defined as the uncertainty in u1, u2, u3, ul. So joint entropy of these u1, u2, ul divided by L. So that's one way of defining uncertainty per letter for a discrete stationary source. Another way of defining this uncertainty per letter is using this conditional entropy. So uncertainty in ul given u1, u2, u3, ul minus 1. So there are two ways in which we could describe the uncertainty per letter for a discrete stationary source. One is this, and the second way is this. Now we are going to prove some properties of these measures of uncertainty per letter, these two, and we are going to show that when L is very large, when L goes to infinity, these two are same. So next we are going to prove some properties of the sequence which comes out of a discrete stationary source. So if u1, u2, un is output of a discrete stationary source, then following relation holds. Uncertainty in ul given u1, u2, ul minus 1 is less than equal to this quantity, uncertainty per letter, which is defined in this particular way. The next property that we are going to prove is this conditional entropy h of ul given u1, u2, ul minus 1. This is a non-increasing function of L. So in other words, uncertainty in, let's say, ul plus 1 given u1, u2, ul, this will be less than equal to uncertainty in ul given u1, u2, ul minus 1. So it's a non-increasing function as of L. Next we are going to show that this uncertainty per letter, this is also a non-increasing function of L. And finally we are going to show that these two different ways of representing this uncertainty per letter, when L goes to infinity, both are same, and this we call as entropy rate of a discrete stationary source. So let us prove these properties one by one. So we will first start with this second property. So let us write this uncertainty in ul plus 1 given u1, u2, ul. Now to show that it's a non-increasing function of L as L increases, so what we need to show is this is less than equal to uncertainty in ul given u1, u2, ul minus 1. So how do we prove it? So first we write down this uncertainty in UL plus 1 given U1, U2, U3, UL. Now this is less than equal to uncertainty in UL plus 1 given U2, U3, U4, UL. So we have removed the uncertainty on U1. Now why is this less than equal to this quantity? We know the property of conditional entropy, that conditional entropy cannot increase the entropy. So conditional entropy of this given U2, U3, UL, and this is conditional entropy of UL plus 1 given U1 and then U2, U3, UL. So this is conditioned on an additional letter which is U1. So this is conditioned on an additional letter U1. So this entropy cannot be more than the entropy of this. And that's why we wrote that uncertainty in UL plus 1 given U1, U2, U3, UL is less than equal to uncertainty in UL plus 1 given U2, U3, UL. Now this quantity can be written because UIs are the output of a discrete stationary source. So uncertainty in UL plus 1 given U2, U3, UL will be same as uncertainty in UL given U1, U2, UL minus 1. So I just, if you recall the definition of a discrete stationary source, what did we say? We said two sources, basically a source is a discrete stationary source if for every n greater than equal to 1 and for every k greater than equal to 1, the distribution of this random vector U1, U2, U3, UL is same as the distribution of this vector UN plus 1, UN plus 2 up to UN plus L. So invoking this property of discrete stationary source, we can then write, because UIs are coming out from a discrete stationary source, we can write this uncertainty of UL plus 1 given U2, U3, UL as uncertainty in UL given U1, U2, UL minus 1. So essentially we are replacing L by L minus 1. If we do that, we get this. And since it is a stationary source, so this distribution and this distribution of will be same. So uncertainty of this will be equal to uncertainty in this. So hence we have proved that the uncertainty in UL plus 1 given U1, U2, UL is less than equal to uncertainty in UL given U1, U2, UL minus 1. So we have proved that as L increases, this term is non-increasing because this is less than equal to this. Okay. Now we are going to make use of this property to prove other properties as well, and that's why I proved this property number 2 first. Now let us try to prove now property number 1. So we can write the joint entropy between U1, U2, U3, UL using chain rule. We can write it like this. So this is uncertainty in U1 plus uncertainty in U2 given U1 plus uncertainty in U3 given U1, U2 and up to uncertainty in UL given U1, U2, U3, UL minus 1. Now from property number 2, we know that as L increases, this term is non-increasing. So in other words, among all these terms, this term H of U3 given U1, U2 and like that. This term, the smallest term is going to be this. Why? Because as L increases, this is a non-increasing. So among all these terms, this term will be the smallest. And there are L such terms. So what we can do is, this summation can be lower bounded by L times of this particular term. And that's what we are writing here. That this joint entropy is greater than equal to L times uncertainty in UL given U1, U2, UL minus 1. So from this we obtain from chain rule, this we obtain by applying this property too. Now we divide both sides by L. So what we get on the left hand side is uncertainty per letter, and what we get on the right hand side is uncertainty in UL given U1, U2, U3, UL minus 1. So then we have proved our property 1, which says uncertainty in UL given U1, U2, UL minus 1 is less than equal to this uncertainty per letter for all L greater than equal to 1. Next we are going to prove this property 3. So to prove this property 3, so let us first write the joint entropy of U1, U2, U3, UL plus 1. So again using chain rule, I can write this as uncertainty in U1, U2, U3, UL plus uncertainty in UL plus 1 given U1, U2, U3, UL. Now, because this particular term is non-increasing as L increases, so this term will be less than equal to this term. So this follows from property 2, which we have proved, that uncertainty in UL given U1, U2, UL minus 1 is non-increasing as L increases. So since this term here is less than this particular term, what I get here is this joint entropy is then upper bounded by joint entropy of U1, U2, UL plus uncertainty in UL given U1, U2, U3, UL minus 1. Now I know from property 1 that this particular term is less than equal to uncertainty per letter, which is HL of U. So then I again can upper bound this by uncertainty in U1, U2, UL plus uncertainty per letter. Now what is this term? This term can be written as L times uncertainty per letter. So this is equal to this plus uncertainty per letter. So this is equal to L plus 1 HL of U. So what we have shown so far is this joint entropy is less than equal to L plus 1 H of LU. Now you divide both sides by L plus 1, what we get is H of L plus 1 U is less than equal to this quantity. So as L increases, we can see this uncertainty per letter, this is a non-increasing function, and that was our property 3, that HL of U is a non-increasing function as L increases. Now we are going to show the final property, which says when L is very large, when L goes to infinity, whether we describe this uncertainty per letter as H of UL given U1, U2, UL, or whether we define this as uncertainty per letter in this particular fashion, as L goes to infinity, they are both same, and this we denote by H infinity of U, which is, we call it entropy rate of a discrete stationary source. So let us prove this. Now we know that this is greater than equal to 0, and this term is also greater than equal to 0. So we have a non-increasing sequence. Remember, these sequences are non-increasing. So we have a non-increasing sequence which is bounded below, because these non-increasing sequences are greater than equal to 0. So they are bounded below. So if you have a non-increasing sequence which is bounded below, then as L goes to infinity, basically they always have a limit. So thus, from the property 2 and 3, which basically says that this particular term and this particular term is non-increasing as L increases. So this ensures that when L goes to infinity, both these terms have a limit which exists. Now, as I said, we have to prove that as L goes to infinity, this particular term is same as this. So how do we prove it? We will first show that one of these terms is less than equal to the other term, and then we will show the other term is less than equal to the first term. So for both of these conditions to exist, then they must be equal. So if you go back and look at property number 1, what is property number 1? Which says uncertainty in UL given U1, U2, UL minus 1 is less than equal to H of LU, uncertainty per letter. Now if you let L go to infinity, then we can write this statement that uncertainty in UL given U1, U2, UL minus 1 when L goes to infinity, this is less than equal to limit L tends to infinity H of LU, and that we are denoting by H infinity U, which we are calling as entropy rate. So this follows from property number 1, and we let L go to infinity. Okay. Now to prove that they are equal, I now need to show that this particular term is less than equal to this particular term. So to prove this, I will do the following. I will first find out the joint entropy of U1, U2, U3, UL up to UL plus N. And using chain rule, I can write this as uncertainty in U1, U2, U3, UL plus uncertainty in UL plus 1 given U1, U2, UL up to uncertainty in UL plus N given U1, U2, U3, UL plus N minus 1. Now what do we know about these terms? We know these are non-increasing as L increases. So among these n terms, like you have UL plus 1 given U1, U2, UL plus 2, uncertainty in UL plus 2 given U1, U2, UL plus 1 up to uncertainty in UL plus N given U1, U2, UL plus N minus 1. So among all these terms, this term is the greatest because we have proved from property 2 that this is a non-increasing function as L increases. So then we can upper bound this joint entropy by, so this term I am writing exactly like this, but this whole summation, these n terms, this one, then up to this term, this can be upper bounded by n times uncertainty in UL plus 1 given U1, U2, UL. And this follows from the second property, which states that as L increases, this uncertainty in UL given U1, U2, UL minus 1 is non-increasing. Fine. The next thing that we do is we divide both left hand side and right hand side by n plus L. So if we divide both by n plus L, what we get is, the left hand side we get this, the right hand side we get this and this. Okay. Now we play a small trick. Instead of letting L go to infinity, we let n go to infinity. Okay. So we let n go to infinity. So if we let n go to infinity, what do we get? What is this term? If n goes to infinity, this is nothing but the entropy rate. Correct? What about this term? Now look at the numerator. This is joint entropy of U1, U2, U3, UL. So this is a finite quantity, this divided by n plus L, where n goes to infinity. So as n goes to infinity, this particular term will go to 0. Okay. Now what about this? This we can write as 1 plus L by n. Now as n goes to infinity, this will become this. So we have shown the entropy rate is less than equal to uncertainty in UL plus 1 given U1, U2, UL. Now we let L go to infinity. So if we let L go to infinity, then basically what we have shown is this entropy rate is less than equal to limit as L tends to infinity, h of UL plus 1 given U1, U2, U3, UL. So note now, here we have proved that uncertainty per letter is less than equal to this uncertainty in UL plus 1 given U1, U2, UL when L goes to infinity, whereas here we have proved that it's the other way around. Okay. Now for both of these conditions to hold true, we would require the condition that both of them are equal, and that proves our fourth property, that as L goes to infinity, uncertainty in UL given U1, U2, UL minus 1 is same as uncertainty per letter when L goes to infinity, and this, as we said, we denote it by the entropy rate. So this is the entropy rate of a discrete stationary source. Okay. Now that we have proved some properties of discrete stationary sources, so let's go ahead and see how we are going to design a block to variable length coding scheme for a discrete stationary source. We have already studied this problem for a discrete memoryless source, and if you recall, we talked about optimal block to variable encoding, which was Huffman coding for a discrete memoryless source. So this problem statement is as follows. We have a discrete stationary source. This is a k-ary source, so it emits k possible outcomes. So these UIs are coming from this discrete stationary source. Now since we are talking about a block to variable length coding, so this source is parsed into blocks of fixed length, and that's blocks of length L. Now these blocks are fed to a prefix free coder. Now since we are talking about sequence that is coming out of a discrete stationary source which has memory, so we need to design a prefix free encoder which will exploit this memory. So that's the difference from a discrete memoryless case. In discrete memoryless case, once we parse them into blocks of L bit, then we are doing prefix free coding. But here we need to do prefix free coding exploiting the memory of the source. And the output of this is my variable length code, which is denoted by Zi. So if block length L messages from a discrete stationary source are encoded using a DRE prefix free code, where the code used for each of the message may depend on previous messages. So why we are saying this? Because our source has memory, so it's probably likely that the sequences which happened in recent past are more likely to happen in future also, as compared to sequences which happened long time back. So we need to design our block to variable length encoder which would exploit the memory of the source, and that's why we are saying that code word used for each message may depend on previous messages. Then we can show that if the length of the ith code word is Wi, then expected code word length divided by input length, this is lower bounded by entropy rate. Okay, so we have already seen this in the context of discrete memoryless source, and we have seen that minimum number of bits per letter in case of discrete memoryless source, this is related to entropy of the source. We are going to show that for a discrete stationary source, this expected code word length by length of this code word block length parser, this is lower bounded by entropy rate. So let us prove this. So let V1, V2, Vi, this is denoted by this particular instance of this. So just a second, let us go back and see the notation. So we are using UIs to denote the output of a discrete stationary source. Now these UIs, you are parsing them into blocks of L bits, and we are using Vi to denote these blocks. So V1 is U1, U2, U3 up to UL. V2 is UL plus 1, UL plus 2 up to U2L. So like that. So Vi is the output of the source parser, UIs are the output of the discrete stationary source, and Zis are the output of your block to variable length coder, which uses memory of the exploits memory of the source. So the length of this code word, output code word Zi, so given you have this particular input to the prefix free encoder, expected code word length given this particular blocks of data V1, V2, Vi minus 1, this is lower bounded by uncertainty in Vi given this particular instance of V1, V2, Vi minus 1 by log D. So this follows from the fact that minimum number of bits, when we are talking about block to variable encoding, minimum number of bits required to represent that source is related to entropy in this particular fashion. Okay, and this we have proved when we talked about block to variable length coding. Now we want to get rid of dependencies on V1, V2, Vi minus 1. So what do? We multiply both sides, probability of V1, V2, V3, Vi minus 1, and sum over all possible values of Vi's. So if we multiply the left hand side by probability of V1, V2, Vi minus 1 and sum over all V1, V2, V3, Vi minus 1, what we get is unconditioned expectation. So we get expected value of Wi, and if we do the same thing on the right hand side, what we are going to get is uncertainty in Vi given V1, V2, V3, Vi minus 1. Next, let us pay little bit attention on this term, uncertainty in Vi given V1, V2, V3, Vi minus 1. Now what is Vi? So Vi is essentially UIL minus L plus 1 up to UIL. So this is a block of L bits starting at this location to this location, right? And what is V1 to Vi minus 1? This is U1, U2, U3 up to UIL minus L. So from the definition of Vi's, we can write this in terms of uncertainty in Ui's. Next, we are going to apply chain rule. So applying chain rule, we can write this as uncertainty in Ui L minus L plus 1 given U1, U2, U3, UIL minus L plus, we will have terms like this, and finally we have uncertainty in UIL given U1 to UIL minus 1. Now again, from the property of the sequences that comes out of a discrete stationary source, we know that as L increases, this is a non-increasing function. So then the smallest term here would be this particular term, and there are L such terms. So this right hand side can be lower bounded by L times H of UIL given U1, U2, U3, UIL minus 1. And of course, as I said, this is non-increasing function as L increases. So this particular term will be less than or equal to entropy rate. So then we can further write that uncertainty in Vi given V1, V2, Vi minus 1 is greater than or equal to L times entropy rate. All right. Now we plug this value here and divide both sides by L. So what do we get? We would get expected value of Wi given L is less than or equal to this entropy rate by log of D, and that's what we wanted to prove. If you recall, that's what we wanted to prove, that for block to variable encoding for a discrete stationary source, expected output code word length by input block size length L is lower bounded by this quantity, which is related to entropy rate of the discrete stationary source. Now we are going to show how we can do block to variable encoding for a discrete stationary source, and to do that I need to first give a scheme which will encode my positive number. So I'm going to talk about a scheme to design coding for positive numbers. So you are all familiar with binary representation of positive numbers. So let's say I have this n, which is 1, 2, 3, 4, 5, 6, 7, 8. So what is this binary representation? 1 is represented by 1, 2 is represented by 1, 0, 3 is represented by 1, 1, 4 is represented by 1, 0, 0, 5 is represented by 1, 0, 1, 6 is represented by 1, 1, 0, similarly 7 is 1, 1, 1, and 8 is 1, 0, 0, 0. So likewise, you can write any positive number by its binary representation. Now, is this a prefix free code? The answer is no. For example, you can see this is a prefix of this code, this is the same thing as prefix of this code. Similarly, this is a prefix of this code, so this is not a prefix free code, right? So if we are designing a block to variable encoding, remember we want for instantaneous decodability, we would like to design a prefix free code. So one drawback of this binary representation of positive number is this is not a prefix free code. Now what is the good part about this binary representation? The number of bits required to represent this number, that's small. So code word length can be given as floor of log n to the base 2 plus 1. So number of bits required to represent the number, positive number, that's small. However, this is not a prefix free code. So wouldn't it be nice to design a prefix free code which would have the number of bits required to encode close to this? So that's the goal. So Elias came up with a scheme to encode these positive numbers. So I'm calling this as Elias code 1. Now what he did here was, so let me show you. So this is my 1, binary representation of 1, binary representation of 2, binary representation of 3, binary representation of 4, 5, 6, 7, and 8. Now what did he have before this? So he had a runs of 0 to denote how many bits follow. So in case of 2, binary representation of 2, it's 1, 0. There are 2 bits that are following. So he denoted by 1 run of 0. In case of 1, there is just 1 bit, so that's nothing. So in case of 3, it's 1, 1. So he denoted that by 1 run of 0. Similarly, 4 is 1, 0, 0. That's 3 bits are required. So he made this binary representation a prefix free code by adding a runs of 0 as a prefix. So by looking at the runs of zeros, you can guess, you can find out how many bits follow this. So for example, if this is 0, 0, then he knows that next 3 bits are the binary representation of the number, right? So you can take, for example, 8. Now 8, the binary representation of 8 is 1, 0, 0. So there are 4 bits. So if you prefix it by 3 runs of zeros, you get what is Elias code 1. So the good thing about this code is it is a prefix free code. And what's the bad thing about this code? That's the length. You are using almost same number of bits, I mean actually the same -1 number of bits to denote the runs of zeros. So as I said, in this particular code, the number of leading zeros are telling me how many digits follow the leading one. There's one more observation you should take note of. When we are writing binary representation of numbers, all of these numbers starts with 1. You see here? 1 is 1, 2 is 1 0, 3 is 1 1, 4 is 1 0 0, 5 is 1 0 1, so like that. So in Elias code 1, number of leading zeros tells how many digits will follow the leading one. So if there are 3 zeros, then after this leading one, there will be 3 more digits that we need to look at. And this leading one followed by the other 3 digits, that's the binary representation of the number that is we are talking about. Now, as I said, the bad part about this code is you are now requiring 2 times floor of log to the base 2 of n plus 1 bit. So the length of the code word is almost double of what was required for binary representation. However, the good part about this code is prefix free. So then how can we design a code which is prefix free? However, the code word length is smaller, especially for large ends. So Elias came up with a trick, and that's as follows. So Elias 2 codes begin with Elias 1 code. So Elias code 1 is used to signal the number of bits in the code word. So earlier what was used in Elias code 1? We were using runs of zeros. So here that is replaced by Elias code 1 to signal the number of following digits in the code word, and followed by the binary representation of the number with leading one removed. As I said, in binary representation of positive number, each of the numbers starts with 1. So that's a redundant information. So what is done in Elias code 2 is you use Elias code 1 to signal the number of following digits, followed by the binary representation of the number with leading one removed. So let us take an example. Let's take this, n equal to 2. So what is the binary representation of 2? That is 1 0. Correct? Now how many digits are there in 2? That is 2, 1, 2. So in Elias code 2, we are going to use Elias code 1 for the number 2, because binary representation of 2 requires 2 bits. As I said, in this particular scheme, Elias code 1 is used to signal the number of following digits in the code word. And in case of 2, there are 2 bits, 1 and 0. So we are going to use Elias code 1 corresponding to 2. And what is that? Elias code 1 corresponding to 2 is 0 1 0. So then 0 1 0 will illustrate or show that. So this is the Elias code 1 for 2, and this is followed by binary representation of 2 with leading 1 removed. So 2 is 1 0, we are removing this leading 1, we are just writing 0. So the Elias 2 code for 2 will be 0 1 0 followed by 0. Take another example. Let's say take this 6. Now what is 6? 6 is binary representation of 6 is 1 1 0. So you require 3 bits to denote 6. That's 1 1 0. So in Elias code 2, which we are denoting by B2 of 6, we first need Elias code 1 of for 3, because binary representation of 6 is 110. So what is Elias code 1 of 3? That is 0, 1, 1. So what we are going to do is, we are going to first write 0, 1, 1. And then this has to be followed by binary representation of 6 with leading 1 removed. So if we remove this leading 1, we are left with 1, 0. So that's your 1, 0. So then Elias code 2 for 6 is 0, 1, 1, 1, 0. So to repeat, we are using Elias code 1 to denote how many digits are there in the binary representation of that number, and then we are following it by binary representation of number with leading 1 removed. Now, what is the beauty of this particular code? Number 1, this is a prefix free code, and let's compute the length of the code word. So remember, the first part of the code is we are using Elias code 1 to denote the number of bits required in the binary representation of the number. So the first part of the code length will be given by L1 of L of n. And the second part of the code is binary representation of the number n with leading 1 removed. So that's why I am writing it as ln minus 1. Okay. Please note, I am using this notation ln to denote the length of the code word for the binary representation of the positive number n. I am using this notation L1n to denote the length of the code word which has been encoded using Elias code 1, and I am using this notation L2n to denote the length of the code word which is encoded using Elias code 2. So the length of the code word for Elias code 2 is, the first part is Elias code 1 of length ln, and the second part is binary representation of the number with leading 1 removed. So its length will be given by this. Now what is L of n? We know L of n is given by floor of log to the base 2 of n plus 1. So if we plug that value of ln here, what we get is the length of this is L1 of this quantity plus floor of log to the base 2 of n. Now what is L1n? L1n, if you recall, L1n is given by this quantity. It is 2 times floor of log to the base 2 of n plus 1. So we have to compute L1 of this quantity. Okay. So then this will be 2 times this plus 1, and this term comes here. So if you compare the length of this code word, Elias 2 code word, is given by floor of log to the base 2 of n plus 2 times log to the base 2 of this term plus 1. Now to appreciate what do we gain by going for Elias code 2. So let's take an example. Let's take n. Let's take n to be a large quantity. Let's just take it n to the power 1048. Let's just take this. Okay. Now in case of binary representation of 1, or binary representation of this number, how many bits are required? We require log 2n plus 1, right? And this, for this value of n, this will come out to be 1048 plus 1, so this will be 1049 bits. But the problem with binary representation is it's not a prefix free. Now if we look at L1n, then the number of bits required is 2 times this term plus 1, right? So this comes out to be then 2096 plus 1, so it is 2097. So it's almost double. Now look at Elias code 2. So here we get 1048, and this will be log to the base 2 of n, so it's 1048 plus 1, I'm ignoring 1, so log of 1049, roughly 1048, so that would be 10, so 2 times 10, that's 20 plus 1. So this is coming out to be 1069. So note, this is a prefix free code, but we are requiring lot less number of bits compared to Elias code 1. Now we can repeat this. We can design an Elias code 3 which will use Elias code 2 to denote the length of the L of n, followed by binary representation of the number with leading one removed. So for large values of n, we can see that if we repeat this process, these are prefix free code and the number of bits required are coming closer to the binary representation of the number. So the Elias code that we just described, we are going to make use of that in our block to variable length coding problem for discrete stationary source. So this Elias-Willems source coding technique is as follows. So we have a discrete stationary source, a k-array discrete stationary source whose outputs are denoted by UI. Now we have a block parser which is creating blocks of these UIs. So Vi is essentially a block of L UIs. Now we will just mention what we mean by recency rank calculator. If you recall, since this is a discrete stationary source, the block to variable length encoding should exploit the inherent memory of the source, and that will be exploited by this recency rank calculator. And since we are talking about block to variable length coding, for instantaneous decodability, we would like to design a prefix free code, and for that we are going to make use of Elias code 2. So the new element that you see here, which is different from what you have seen for block to variable length coding for discrete memoryless source, are these two blocks. Okay. So we are using a prefix free code, however, we are exploiting the memory of the source, and we will tell you in a little while what do we mean by recency rank. So the message that is seen most recently has recency rank of 1, then next different message most recently seen has recency rank 2, and so on. So recency rank is essentially an indication of how far in the back, like in the past, you have encountered that particular sequence. So let us consider a very simple example. We are considering a block of length 2, and let us consider a binary discrete stationary source. So then UIs are essentially zeros and ones, and since my block length is 2, so the possible outcomes possible VIs could be 0, 0, 0, 1, 1, 0 or 1, 1. Now, what this recency rank calculator will do is, will look at the occurrence of these among the past sequence, and whichever sequence occurs most recently will be given a recency rank of 1, then the next one will be given recency rank of 2, the third one will be given recency rank of 3, and similarly the last one will be given recency rank of 4. So let us consider that this is a sequence that you have encountered in the past. So this is Vi minus 1, this is Vi minus 2, this is Vi minus 3, Vi minus 4, and so on. Now, which among these 4 sequences have occurred most recently? That is 0, 1. So 0, 1 will be assigned a recency rank of 1. So message 0, 1 will be given a recency rank of 1. Let me write back the sequences. So this has recency rank of 1. Now next, 0, 0 occurs in the past. So this will have a recency rank of 2. Then 0, 1 already has a recency rank of 1. Next sequence that we see is 1, 0. So this will have a recency rank of 3. And then you have 1, 1. So this will have the recency rank of 4. Okay. So this is how we are assigning a recency rank. So this block that I mentioned is essentially emitting a positive number, and that's an indication of how long in the past that particular sequence has occurred. So as I said, 0, 1 has a recency rank of 1, 0, 0 has a recency rank of 2, 1, 0 has a recency rank of 3, and 1, 1 has a recency rank of 4. Now, what this Elias code will do is, it will code these positive numbers, and the resulting code is going to be a prefix free code. And the memory of the source is exploited in this recency rank calculator. So what we are essentially assuming is the sequences that appeared in recent past are more likely to appear in the future, and that's why they have been given a smaller recency rank. So if we encode those positive numbers, because the sequences which happened in recent past will have smaller recency rank number, so when we will encode them using B2 code, the expected code word length would be smaller. So in the Elias-Willems source coding scheme, this recency rank calculator assigns a recency rank to the message Vi, which is a block of L bits. So now we are going to calculate what is the expected code word length per input block length for this Elias-Willems source coding technique. So we are going to show you that for a Elias-Willems source coding technique, where input is of block length L and we have a carry discrete stationary source, the expected code word length divided by L is upper bounded by this quantity. Okay. And if L goes to very large, you can see these terms becoming smaller and smaller. So this term is coming closer to entropy rate plus some small term. So let us define delta I as the recent occurrence of the message Vi. So delta is this delta where if Vi is V, then Vi minus delta is the most recent past where this particular message has occurred. Okay. Now, let us go back to this example. Okay. So, let us say Vi is 0, 0. So, we have to go back in the past and see when did 0, 0 occurred. So, you can see this is Vi minus 1, Vi minus 2. So, this is delta corresponding to 2. So, delta I in this case will be 2. Now, if you consider 1, 1. So, when did 1, 1 occurred in the past? I minus 1, I minus 2, I minus 3, I minus 4, I minus 5, I minus 6, I minus 7. So, delta I is going to be 7. So, that is what I am saying, that we define this time delta I as the recent occurrence of this message Vi. So, if delta I is equal to delta, if Vi is V, then Vi minus delta is the most recent past when that particular value of V has occurred. Now, you can see clearly that delta I is going to be greater than the recency rank, right. So, what is the expected code word length? The expected code word length is given by the length of Elias code 2 of Ni, the recency rank. Now, we have just now shown that this recency rank Ni is less than equal to delta I. So, this code word length Wi is upper bounded by the length of Elias code 2 of delta I. Now, we know what is the length of the Elias code 2. This is given by, if you just go back and refresh your memory, this is given by this expression. Now, if I remove these floors, I can write length of Elias code is upper bounded by log to the base 2 of n plus 2 log to the base 2 into log to the base 2 plus 1 plus 1. So, that is what I am doing here. Okay. So, this follows from the length of the Elias code, correct. Next, there is one thing which I skipped, which is what is the expected value of delta I given Vi is V. So, that is inversely proportional to the probability of occurrence of V. So, that is basically given by this. Now, we take conditional expectation of Wi given Vi is V and we invoke Jensen's inequality. So, if we take conditional expectation of this on the left hand side, what we will get? Expected value of Wi given Vi is V. So, that is this term. Now, if we take conditional expectation of this, so this will be expected value of log to the base 2 of delta I given Vi is V. Now, what do we know about log? Log is a concave function, and if it is a concave function, what do we know? From Jensen's inequality, we know if it is a concave function, then expected value of the function is less than equal to function evaluated at expected value. So if we take conditional expectation of delta I, log of delta I to the base 2, given Vi is V, since log is a concave function, we can say expected value of this log function will be less than equal to log evaluated at expected value of delta I. So that's why you see here. So there are two steps involved here. We are first taking conditional expectation of this term. So we are taking conditional expectation of this given Vi is V. Next what we are doing is, since log is a concave function, we are saying expected value of the function should be less than equal to function evaluated at expected value of x. So what is the function? Function is log, that's this. And what is expected value of x? So expected value of x in this case is expected value of delta I given Vi is V. Okay. So what we did was, we did two things here. We took conditional expectation, condition on Vi is V, and we invoked Jensen's inequality. The same thing we'll do here for this particular term. We first take conditional expectation of this given Vi is V, and since log is a concave function, then the expected value of the function is less than equal to function evaluated at expected value. So that's why we move the conditional expectation inside, and we can write this as 2 log of expected value of delta I given Vi is V. Okay. Next, we know what these terms are. From the ergodic property, we said that this is given by this. So we plug in the expected value of delta I given Vi is V into this expression. So if we do that, we will get this. Now we need to get rid of this conditional expectation because we want to get the value of expected value of Wi. So to do that, what we do is we multiply this particular expression, we multiply by probability of V, and then we sum over all V's. Okay. And another thing that we are going to use is we are going to make use of Jensen's inequality. So when you multiply the left hand side with probability of V and sum over all V, we will get unconditional expected value of Wi. Now look at the first term on the right hand side. If I multiply this by probability of V and sum over all V, what I am going to get is uncertainty in V, right? Now look at this particular term. If I multiply this by probability of V and sum over all V, this is like taking expectation of log function. Now this, since log is a concave function, I can again say that expected value of the function will be less than equal to function evaluated at expected value. So what I am going to do is, I am going to then, by invoking Jensen's inequality, I can write this as 2 log of, I multiply this by P of V and sum over P of V. So this particular term that you see here will become uncertainty in V. This comes as it is and this one comes here. Alright. So Again I used two things. I multiplied both sides by probability of V, sum it over all V, and I invoked Jensen's inequality, which says that if you have a concave function, then expected value of the function is less than equal to function evaluated at the expected value. And that's what I used here. Now, let's pay attention to this particular term, h of v. Now, h of v is what? What is v? V is this block of L bits which are coming from a discrete stationary source. So, h of v is nothing but uncertainty in u1, u2, u3, ul, and this I can write in terms of uncertainty per letter, that L times h of Lu. Now, in this particular expression that I derived, I am going to replace h of v by L times h of Lu. So, if I do this, I get this expression that expected, and I divide by L throughout, I get this expression that expected code word length per input length per input bit is upper bounded by this quantity. So, this gives us a upper bound on expected number of bits required to encode the sequence which comes out of a discrete stationary source. So, this is just one simple example to illustrate how we can exploit memory to encode a source which has memory. So, with this we will conclude our lecture on coding for sources with memory. Thank you.